Hello again, everybody. Welcome back to day 2 of e-learning. Hope you enjoyed day 1 as much as I did. Day 2 will be just a little more of Polar. There are 3 days of notes. So we've done day 1 already. Today's day 2. Tomorrow's day 3. If I can figure out a way to make an online quiz happen, that would be on Thursday. So just be prepped for that. I'll let you know tomorrow probably if I've been able to figure that out. And it would just cover the 3 days of notes right on the schedule that you would have been given at the beginning of the chapter. So 2 main things today: graphing in polar coordinates equations, and taking the derivative of polar functions. So you'll see here the steps are outlined for you at the top in terms of how we're going to do this. First thing it says is set up an R theta chart. So it's kind of old school. When you would have first learned how to graph in terms of XY, you would have set up an XY chart. We're setting up what we're going to call an R theta chart. We basically just start kind of at angle 0 here and then work our way around pi over 6, pi over 4, pi over 3, pi over 2. So we'll definitely start at 0. And what we want to think of is, all right, if I come over to this equation, let my theta be a 0, what sort of R value do I get? So we get 1 plus 1 here. So we would know our R is a 2. So that's the first point on our graph. If we look at the 30-degree angle here and the 60-degree angle here, for the sake of what we're going to be doing, I wouldn't worry too much about finding both of them. Let's pick the one that's going to give us a nice cosine value. So in this case, the nice cosine value is going to be pi over 3, because we know when we plug in pi over 3, that the cosine value up there is a 1/2, so we can say that this is 1 plus 1/2. So at pi over 3, we know our radius is 1.5. So if we look up at this angle, if we go to 1.5-ish, we know that's where we're going to be. Now, we do want to do pi over 4. We don't want to skip too much. So if we went ahead and plugged in pi over 4, I don't know why that pops up all the time. Oh my gosh. Get out of here. So plug in pi over 4. This is something you'd want long term, depending on how you're going to take this quiz, want to just have memorized. In terms of a value, we obviously know that that's root 2 over 2. Root 2 over 2 is approximately 0.7-ish for the sake of our graphing. So if I did 1 plus 0.7, looking at angle pi over 4, we're right about here. If we went ahead and did finally pi over 2, let me create some space here, erase cosine of pi over 2. The x-coordinate at pi over 2 is going to be a 0, so our radius ends up being a 1. And then we can connect with, let me try that again. So then we connect this, and we would have that part of our graph. We basically just continue on. So now this is a good unit circle review. We're going to have to come up here to this angle, 2 pi over 3. Erase this. And then evaluate cosine of 2 pi over 3. Oh boy, think of this myself. So cosine of 2 pi over 3 is a negative 1/2. So that value when we're at 2 pi over 3 is 0.5. So looking at that angle, but very tiny little guy here. If we did 3 pi over 4, the 45-degree angle in quadrant 2, we would have had, so what, 3 pi over 4 is a negative root 2 over 2. So again, root 2 over 2 up here is 0.7, so this would be a negative 0.7. So 1 plus that negative 0.7 should be 0.3, so even tinier, really tight in there on that 45 degree angle. That kind of looks like it's on the 60, or the 30, but this should be 45. We're going to get the pi over 6 and then jump to pi. So if I went to pi, time, here's pi, throw that in, cosine of pi, -1, r is a 0. So what that means is we look at angle pi, this might be the first 0 radius that we've had. It means we're looking in this direction of pi, just like we would have done yesterday for the sake of graphing. So we look in that direction. But we don't go anywhere, so we pretty much just stop right there so that this circles around. If you're in class, had time to kind of go over this a little bit more, I would probably go ahead and just finish off this by going, all these third quadrant angles, 7 pi over 6, what is that, 5 pi over 4, oh man, I gotta remember all my stuff here, 2 pi over 3, 4 pi over 3, so on and so forth. We just go all the way around, but what you're going to notice at the top of the page, number 4 is a big one, where it says recognize some symmetries around the x and the y axes. That will help with our graphing a little bit, save some time so this doesn't become too tedious. What you'll want to know is that any cosine curve is going to have symmetry to the x-axis. So that means if I look at this, here's your x-axis. If I now just reflect this curve around the x-axis, so that means we're going to go through a -1 here, kind of do something like this, create that reflection around the x-axis, then we end up with our graph. That'll save you some time. So that'll tell us if we're symmetric to the x-axis. As long as we know quadrant 1, quadrant 2, then we just basically flip our graph around the x-axis and we have the rest of it. We'll do one here in a second. This will be a sine curve, so you can probably guess what that would mean in terms of symmetry. If I have a sine curve, that means we're going to be symmetric to the y-axis. Since we're going to be symmetric to the y-axis, come on. What we would want to make sure or be able to do is just get what's happening in the first quadrant and the fourth quadrant. Because if I can figure out what's happening here, if we're symmetric to the y-axis, we would just take this, reflect it around the y-axis. That would be our graph. So with this one now, if we just want first and fourth quadrant, when we go to set up our r theta chart, and first quadrant we still want, so we're still going to pick 0 just for the sake of being safe, or I shouldn't say safe, but just easier, efficient, quicker. Pick pi over 3 or pi over 6, whichever one is a nice value. For the sine, pi over 6 is nice because that's where you're going to get your 1/2. Come on. So we're going to pick a 1 or pi over 6, and then we'll pick pi over 4. And then we'll pick pi over 2, and that'll get us through our first quadrant. So we're just, again, plugging in. Break this up. So r is 1 minus sine of theta. So take your 0, plug it in. Sine of 0 is 0. 1 minus 0 is 1. So it tells us we look at angle 0, we're going to go out for a radius of 1. If we go to pi over 6, so you're now going to plug your pi over 6 in. The y-coordinate at pi over 6 is 1/2. We would then have 1 minus 1/2. So that's a half. So when we look at the pi over 6 angle, we're just half on that. We're back to our pi over 4, which we know up here is our 0.7. If we did 1 minus 0.7, we're talking 0.3. So even tighter right here. And then if we did pi over 2, try to write over this. This becomes a pi over 2. The y-coordinate pi over 2 is a 1, so I'd have 1 minus 1, which is 0. So make this little connection here, and then that's the first quadrant. If we now keep in mind that we're symmetric to the y-axis, we can now get the second quadrant value by just coming over to the other side and doing a little symmetry. Pretend like that's symmetric. It's not easy drawing with this pen, so looks something like that. We would then need fourth quadrant, and then whatever I get in the fourth quadrant reflected around the y-axis, that's going to produce the third quadrant. So you can go either or. You can call this 11 pi over 6, this angle here 11 pi over 6. I think it's probably easier to think negative pi over 6, because then you can actually kind of look back at your table. We know pi over 6 is a 1/2 positive. The y coordinate down here then would have to be a negative 1/2. So let me write this in here. If I went ahead and plugged in negative pi over 6, then let me clean this up a little. What that would give me is the r would equal 1 minus, and then the y coordinate down at a negative pi over 6 would have to be a negative 1/2. So that we'd be looking at 1.5. So we go to 1.5 along the angle negative pi over 6. We do negative pi over 4. So let me just try to write over this. Pretend now that's a 4. We know pi over 4 is 0.4, or excuse me, 0.7. Since it's a negative, we would have a negative 0.7. So we're at 1.7, looking at this angle, pi over 4. In the fourth quadrant anyway. And then we'll skip that pi over 3, negative pi over 3, sort of unnecessary for just sketching out what we're trying to create. If I go to a negative pi over 2, our y coordinate down at a negative pi over 2 would be a negative 1. So our radius would be 2. Connect these, swing that around like so. That's pretty bad. Hopefully you're a better drawer than I am. This should look like a heart. It's actually called a cardioid. Both of these guys, well, this one is sort of rotated 90 degrees. This one actually looks a vertical, but these are both what you would call a cardioid, which I think you do a little bit in Math 3 these days. All right. Next couple will be interesting. Little curveballs here. But 3 in particular is pretty important. You're going to want to recognize some things that go on here. So just a little review from the top. Since this is a cosine graph, that means we're going to reflect around the x-axis. So if we can go to quadrant 1, and we can go to quadrant 2, figure out what's going on in those 2 quadrants, then we can just flip that around the x-axis and have our graph. So when we set this up, we really just need to go through the first quadrant. So definitely angle 0. Keep in mind the nice, pi over 3 or pi over 6 angle for cosine. The one that's going to give us a 1/2 is up at pi over 3. So we're going to skip the pi over 6. We'll pick pi over 4. We'll use pi over 3, pi over 2. So it'll get us through our first quadrant. And then the pi over 3's we like, so we're going to keep 2 pi over 3 in the second quadrant, 3 pi over 4 in the second quadrant. We'll skip that 5 pi over 6 and then go down or over to pi. This should tell us what's happening in the first, second quadrant. Once we have that, connect them, flip it around the x-axis. So plug away. But some interesting things will be happening here, so just be careful with this. If I plug in a 0, cosine of 0 is going to be a 1. So at angle 0, our radius is 3. And, if we go to pi over 4, let me put that back up here now. It's about a 0.7. So this would be 1 plus 1.4. So this would be 2.4. So at the pi over 4 angle, we're looking at about 2.5-ish, just inside 2.5. If we pick pi over 3. Oops. The reason we picked pi over 3 is because it's our nice 1/2. So you'd have 1 plus 2 times 1/2. So 1 plus 1 is 2. So it takes us to 2. And then at pi over 2, oh gosh, 0. So then our radius is 1. And so graph would look kind of like this. And if we know that, then we can come down here, create a reflection, and then that's half of our graph. So far it looks similar, but some interesting things will happen next when we go into the second quadrants. Take your 2 pi over 3, plug that in. At pi over 3, we know it's a half up here, but it's going to be a negative half because we're in the second quadrant. So what we would end up with is 1 plus a negative 1. So right away we get that angle 0. So think about the domain here. We went from pi over 2 up here directly to 2 pi over 3. That's the next angle in our domain. So this makes a pretty sharp turn right into the origin. So that's going to be important. If I then do 3 pi over 4, this 3 pi over 4 is again our negative 0.7, which gives us a negative 1.4. We add those, our ends up being a negative 0.4. So the first time with one of these, we've had a negative value. So you are looking at 3 pi over 4, just like the negative angles that we did yesterday. That's the direction you're looking at. However, even though we're looking at that angle, we actually go backwards. This too. We actually go backwards 0.4. So that would mean along this 45-degree angle here, we are half a unit away. And then that means we went here. There, that's pretty good actually. If we pick pi, clear some space. The cosine of pi is a negative 1, so we'd have 1 plus negative 2. Our r is a negative 1. So we're looking out here towards pi, but we go backwards 1. So that takes us to right here. If we now do that reflection, so you have this little arc in here. If we reflect that around the x-axis, it looks like this. And then this little part up here would reflect down here, and we get that guy. These types that have a little loop in them, fairly common questions, fairly common in terms of things we've got to do with them, but that's something that you want to be familiar with. Last one, r equals cosine of 2, r cosine theta equals 2. For us to actually set up our r theta chart, we'd have to solve this guy for r. So we would do 2 over cosine of theta. It's a cosine graph, so we're going to go, we're symmetric to the x-axis. So we really just need, again, quadrant 1, 2, and then we can reflect that. So we're going to pick 0. Yeah, we'll skip pi over 6, pi over 4, pi over 3, and pi over 2. This is kind of cool what's going to play out here. Take your 0, plug it in. Cosine of 0 is 1, so we'd have 2 over 1, which is 2. So looking at angle 0, we're out here at 2. Come across our pi over 4 again. We know the cosine of pi over 4 is root 2 over 2. So what this would give us is 4 divided by root 2. Let me approximate that for you. 4 divided by 4, about 2.86-ish. So go to this angle here. Here's pi over 4. You're going to go out to 2.86, so right about here. Okay. If we go to our next one, two over cosine of theta. Our angle in this case is pi over 3. So that would be 2 divided by, and then we know up here the cosine of pi over 3 is our half. So our radius is 4. So if we look at the pi over 3 angle, we're up here at 4. All right. What you should notice, and we could do some more of these, but we also should reflect this. So if I go to the pi over 4 angle down here, this would be negative pi over 4. Oops. I've got to be out here at 2.86. If I go to the negative pi over 3 angle here, I've got to be out here at 4. And what you would see, notice how these are all lining up into a nice vertical line. If you recall what we talked about yesterday, you would remember that this here is a conversion from polar to Cartesian and vice versa, that this r cosine of theta is equivalent to x. So we really just have x equals 2, which is the equation of a vertical line. So it's no coincidence then that we get a vertical line through here. It'll be a segment in terms of domain. You're going to have some discontinuities in here as we go through it. But by and large, you just have a vertical line going up and down because of this conversion that we dealt with yesterday. Okay, so that's how we can graph. Next thing you're going to want to be able to do is find the derivative of polar equations. It's actually kind of similar to what we just quizzed over with the dy dt over dx dt is equal to your dy dx. So as you kind of look at this, you're going to recall a couple of things. One from yesterday, we just talked about it. X is equal to r cosine of theta, and then y is equal to r sine of theta. So to find dy dx, similar to what we would have done in parametric, what we really got to do is take the derivative of this one. So if we took the derivative of this, this would produce for us a dy over d theta. If we took the derivative of this one, this would produce for us a dx over a d theta. So similar to parametrics, in order for us to get dy over dx, we would want to create this ratio here. Take your dy d theta, divide it by your dx d theta. The d thetas cancel, and we would just end up with dy over dx. That's what we have here. So now, you'll see kind of an ugly little derivative formula here. But all this dy dx is really asking us to do, or telling us we need to do, is take the derivative of y divided by the derivative of x. Dy d theta divided by dx d theta. If you want to remember this, that's fine. But what's really happening here is we are taking the derivative. So let me rewrite y here. So we know y is equal to r sine of theta. So if we took the derivative of this, dy d theta, notice how you have a little product here? This is nothing more than the product rule in our numerator. So if I ask you to take the derivative of this, you would do r prime sine theta plus, then leave r alone. The derivative of sine is cosine. So if you look at this expression, that's where your numerator has come from. It's really nothing more than the derivative of r sine of theta. Okay. Then what we've got to do is divide that by the dx d theta here. So if we remember what x is r cosine of theta. So that if we took the derivative of this, dx d theta would equal, product rule again, the derivative of the first term would be r primed. Leave cosine of theta alone. Initially with the product rule you would add, leave r alone. The derivative of cosine then is a negative sign. So because it is a negative sign, it would change this plus sign to negative, and then our cosine of theta. That's where your denominator comes from. So it's really just taking the derivative of y here, the derivative of x here, and then dividing those, dy d theta divided by dx d theta to get our dy dx. All right. Some people over the years have memorized this big, long, ugly formula here. If you want to memorize that, that's fine. I think the safe way, you're going to have to know these conversions up here. All right, that's something you'd be tested on in and of itself. And if you know that, then you would know the derivative would just be the derivative of y divided by the derivative of x. That's going to give us that ratio dy over dx. Okay. So with that said, let's move along. We'll probably just do one or two of these, or just one of these two, because they're kind of a pain. As you can see, it's kind of long and drawn out. I never honestly got this memorized. I don't really spend time memorizing it. What I just remember is that here's what x is, here is what y is, and if I just remember how to take the derivative of those, then we should be good. So if we look at this here, what we're going to need for our formula, we need r primes and we need r's. So we have r, that's your original equation here, but we would also need some r primes. So we're going to take the derivative of this, r primed, and we would get a negative sine of 2 theta and then times 2. So that's r primed. If we then go to our derivative, dy dx should equal the derivative of r sine of theta. So the derivative of r sine of theta is right here. So this we're just rewriting now in the numerator. So we would have r primed sine of theta plus r cosine of theta. Make a better r here, hopefully. All right, then we divide that by the derivative of our cosine, which is this mess. And we just, again, do that from the product rule. So that would be r primed cosine of theta minus r cosine of theta. Did I mess that up? That doesn't look right. Yeah, let's go back. See, nobody can raise their hand and tell me I screwed up here. So the derivative of this, r's derivative is r primed. Leave cosine alone. Then you leave your r alone. The derivative of cosine should have been a negative sign. So let's go back and fix this. Sorry. And then come down here. And fix this. All right. Then what we now have to do for this one is we need to evaluate this at the theta value of 0 and then pi over 2, pi, so on and so forth. So this slope, first we're going to take what r primed is. These are messy, by the way. You can see a lot of space I left for you to work with. You're going to take your r primed and you're going to substitute in what we have r prime to be. So instead of this r prime, we're going to replace it with what we found our derivative to actually be. So negative 2 sine of 2 theta and then times sine of theta. Plus, take your r here, and we know r is cosine of 2 theta times cosine theta. Divided by, again, r primed. Here's r primed. So negative 2 sine of 2 theta again. And then we do our cosine of theta minus r. R is the original problem. So cosine of 2 theta. And then times a sine of theta. All right, you can see, kind of ugly. Still evaluating this at 0. You do typically get some nice numbers here, because think about what this would look like if you had to evaluate it like pi over 6 or pi over 3. It'd be a nightmare. But 0 should be pretty simple. So now we're going to find our slope when all of our thetas are zeros. And you'll see good stuff would happen. So here, we have a negative 2. The sine of 0 would be 0. We have another sine of 0. So that's going to be 0. Uh-oh. Get out of here. Oh, man. Oh, man. All right. Plus cosine of 0 would be a 1 times another cosine of 0, which is a 1. So what we see is our numerator is a 1. In your denominator, we would have negative 2. Maybe if I can get it right, negative 2. And then again, sine of 0 is 0. Cosine of 0 would be a 1. Minus cosine of 0, 1. Sine of 0, 0. So what we end up with in our denominator is a 0. So this slope ends up being undefined. That should make sense. The reason that should make sense, think about what all these graphs look like previously. A lot of different reasons we could get, not a lot, but 3, where we could get our derivative be undefined. One of them, that probably the one that we see the least and have dealt with the least, is vertical tangents. So if you look at those first 3 that we did, you can see there's vertical tangents all over the place for all of those. So if we look here, we'd have vertical tangent here, vertical tangent here, vertical tangent here. This one down here is vertical tangents all over, a couple here, a couple there, one by the loop. All kinds of issues going to be going on with these. So all of those places on our curve are going to have slopes that are undefined, and that's what this one is telling us. If we were to graph this at 0, we'd have a vertical tangent line, and that's what's making our derivative undefined. Okay. Again, if we had time, if we were in school, class, we'd probably go ahead and throw those in real quick. But for the sake of having to listen to a boring presentation over the internet, we'll go ahead and skip those. Really what we're just now doing is taking your pi over 2's, plugging them into this formula. So we would just kind of go back to here, just so we have a different number. We would now evaluate pi over 2. So we would just change up all of these guys just to give yourself a different slope. Okay. 2, we'll go through just to make sure we understood where that big, long, messy formula came from. So I'm going to erase this because I know if you aren't caught up yet, you can pause me. So let's get rid of all of this. Oops. So we have a little room to work for number 2. All right, so up to you how you're going to do this. Again, one thing we can do is just know up here, so I'll do this in red, no r, or excuse me, no x, no r, and know that we have to take the derivative of r, divide it by the derivative of x. That's where our formula would come from here. Or you can just get this memorized. It'll always be the same initially. What will change is r primed. So in this one, r primed is just what? Negative 3 cosine of theta. If we take our formula here, so let me create a little space here. So dy dx is r prime sine theta plus r cosine of theta divided by r prime cosine of theta minus r sine theta. So in this one now, when we do our substitution, let me get rid of this. Not sure how that happened. Dy dx would equal r prime. Here's our r prime for this one. So negative 3 cosine of theta times this cosine of theta. I'm sorry, sine of theta, plus r. So here is our r2 minus 3 sine of theta, and then times a cosine of theta, divided by r primed, so negative 3 cosine theta, and then cosine theta, minus r, so 2, what in the world? I don't know how that just happened. 2 minus, so we're here plugging in for r, so 2 minus 3 sine of theta times sine theta. All right. Let me expand this out maybe, hopefully. maybe not. And then we're just going to have to evaluate this at pi over 2. So let me sneak that in there. So we're going to evaluate this whenever our thetas are pi over 2. So we'd have in the numerator -3, and then we'd have here the cosine of pi over 2 is 0. The sine of pi over 2 is 1. Plus 2 minus, and then we would have 3, and then the sine of pi over 2 is 1. But this cosine of pi over 2 gives us another 0. So our numerator is 0. In the denominator, -3. Cosine of pi over 2 is 0. So both of those, we're going to get 3 times 0 times 0. Minus 2 minus 3. And then we know what's the sine of 0, which is 0. I'm sorry, 1. Make that a little nicer. Go away. So that's a 1. And then again, another sine of pi over 2 is a 1. So we would get these to go away, but we would get a negative 1 times 1. So our denominator is 1, so this slope is 0. If we go back to the graph, we can see lots of places where we have slopes of 0. Slope of 0 here, slope of 0 here. Even here we have slope of 0. There we've got a slope of 0. So a lot of horizontal tangents as well with these, and that's what we have just found. Okay. All right. Last but not least, it says find all locations for all vertical tangents, or find the location for all vertical tangents to the cardioid 1 minus cosine of theta, where theta lies in between open interval, so we're not worried about our endpoints. That is important. In between 0 and 2 pi. So now what this is giving us is, all right, this is going to be a cardioid. If we were to graph that, where do we get vertical tangents? So we've talked about this in the past. We haven't had to really deal with it too much. Vertical tangents, you want to start making some connections. What that hopefully then means, that tells us, is that our derivative, let me do this where we can keep this. I have to erase it all. So the idea that we have vertical tangents would mean that our derivative, so dy dx, is undefined at vertical tangents. So that's kind of our first thought. Second thought then would be, all right, if our derivative is undefined, that would mean our denominator, if I can fit that in there, would have to equal 0. And then that would give us the next thought. In a derivative for polar, it's dy d theta divided by dx d theta. So what we are basically saying is dx d theta would have to equal 0, because that's the denominator when we do these. Okay, so x is our cosine of theta, and dx d theta, just a product rule. So this would be third or fourth time we've done this now. R primed, leave the cosine theta. Initially, again, we would have said plus because it's a product rule. You would leave the r alone. But then the derivative of cosine is negative sine of theta. And what we then want to know then, since that's our denominator in our derivative, we want to know when would this equal 0. All right. So r primed we need. R primed is positive sine of theta. So take r prime, substitute it with sine of theta, times cosine of theta, minus r. So r in this case is 1 minus cosine of theta, and then times sine of theta, and then that's going to equal 0. So trig equation, probably the most involved trig equation we've dealt with this year. We want to clean this up. So do that. So we get what? Negative sine of theta plus sine theta cosine theta equals 0. You would then see that we have like terms here. We have 2 sine theta cosine thetas, so we're going to put those together. Still have our minus sine of theta, and then that would equal a 0. We solve this like we do a regular quadratic equation. We're going to factor out that sine of theta. We'd be left with 2 cosine of theta minus a 1 equaling a 0. And then it's just some old zero product property stuff where we're going to take that sine of 0, or sine of theta, figure out where that equals 0, and then take the factor of 2 cosine of theta minus 1, set that equal to 0. So one set of solutions will solve this equation, sine of theta equals 0. The other one are the solutions that satisfy this equation. So with this trig function, we're going to solve for cosine of theta. We'd add the 1 over, divide by 2. So we're trying to solve these two little trig equations. So what this would give us is what angle, we have to stay open interval 0 to 2 pi, would our y, what angle would our y coordinate be a 0? So those angles, those thetas, would be 0, pi, 2 pi, normally. But if we consider the interval and how it is an open interval, 0 and 2 pi can't be answers. We don't want 0, we don't want 2 pi, but pi is a solution. If we then go to cosine of theta equals a 1/2, we're trying to think, okay, in the interval of 0 to 2 pi again, what angle would have x coordinates, cosine values of 1/2? So those angles would be, I gotta think about this myself, pi over 3. That's our first quadrant angle who has an x coordinate of a positive 1/2. And then also in the fourth quadrant, we would have a pi over 3 angle with an x coordinate of 1/2. In the fourth quadrant, pi over 3 angle is 5 pi over 3. So our answers are pi, pi over 3, and 5 pi over 3. Okay? So these three. All right, a little bit longer one today. Hopefully you're able to keep up there, follow all of this. We will hopefully, if I can figure it out, not real sure if I can, especially with this material, have a quiz on Thursday, just as planned on that schedule. So hopefully that will go reasonably well. If not, we'll figure out something else to do. More than anything, keep up on the notes. When we come back, hopefully if it is after spring break, if you keep up with the notes yesterday, today, what we're going to do tomorrow, I'll get you the review by the end of this week. You would have everything that you would need to make sure that come Tuesday after spring break, we're able to sit down and take that test. So good luck with all of this. If you have any questions, reach out, let me know. Hope you're enjoying your time off. We'll talk to you guys later. Bye.